Hello, everyone. This is Volts for May 8th, 2026. The case for using prices rather than VPPs to coordinate distributed energy. I'm your host, David Roberts. The electricity grid has more and more participants. There are increasing numbers of small distributed energy resources, or DERs, solar panels, home batteries, EVs, EV chargers, hot water heaters, commercial and residential HVAC systems, and on, that need to be coordinated to work as efficiently as possible for the good of the grid as a whole. But how should they be coordinated? One answer, which I have discussed many times here on Volts, is what are called virtual power plants, or VPPs. This involves a single aggregator, usually but not always a private party, contracting with dozens, hundreds, or thousands of distributed energy device owners, agreeing to control and coordinate their device's behavior, monetize the flexibility, and share the value with the owners. My guest today, Bruce Nordman, spent nearly 4 decades as a research scientist at Lawrence Berkeley National Laboratory, working at the intersection of network technology and energy systems, and he thinks VPPs are the wrong answer. Not because they don't work, they do, but because the gap they're exploiting between the real-time locational value of electricity and the flat, time-invariant rates actually charged to customers shouldn't exist. If retail electricity prices actually reflected real-time value, there would be nothing to arbitrage. The flexibility value currently being split with aggregators would just stay with customers, captured automatically by their own devices, without any private third party reaching in their home to do it. The technologies needed to do this, basically a central price server to send the price signal and devices capable of responding to it, have become cost-effective on a mass scale in recent years, and there are limited experiments underway in some places running things this way. In this conversation, Nordman and I dig into it pretty deeply. Okay, very deeply. This is an intensely wonky discussion, more technical than most of what happens here on Volts. But if you are a real head and you want to understand how to actually get the most out of distributed energy resources, I think it is ultimately fascinating and worth it. With no further ado, Bruce Nordman, welcome to Volts. Thank you so much for coming.
Well, thank you.
This is a lot, Bruce, and I've been thinking about how to ease into it. So kind of where I want to start is at the big abstract level. So like when you first approached me with this, you're like, hey, let's use prices instead of VPPs. I had in mind like, you're going to design some novel tariff for PJM or something, something like that. But this is much bigger than that. This is a sort of ground up new vision for how electricity works. So it's a little bit more to get into. And part of the big vision here is similar to Jonas, who we talked to a couple of weeks ago, Jonas Bergeson, in that this is about transitioning the electricity industry from the old unitary model to a networked system. That's what I talked with Jonas about. This is, I think, an excellent adjunct to that, or a sequel, or I don't know exactly what you'd call it, but you're involved in, broadly speaking, the same project. So you write that the telephone system and the electricity grid were invented roughly the same time, roughly the same place. So they are interesting kind of analogs to track. And as listeners know at this point, we covered it a little bit on the Jonas pod, the telephone system has now entirely been transformed into the internet. And this involved, as I said, going from a unitary system to what's called a networked system. And the electricity grid, notably, has not. And so one of the things I want to talk about starting up front is some of the aspects of what it means to go from a unitary to a networked system. And then so we can look at sort of how the internet did it and how the electricity grid has not done it. You have this chart here of like sort of qualities of a unitary system and then qualities of a network system. A lot of this, I think, people understand intuitively. So you're going from a centralized system to a distributed system. You're going from a largely analog system to a largely digital system. But here's one that I want to look at because I think it's important for understanding the electricity grid and why it's such a problem. One of the things that the telephone system did is go from a tightly coupled systems to loosely coupled. So just briefly, and keep in mind briefly, because we've got a lot of territory to cover, just briefly, talk about what it means for systems to be tightly coupled or loosely coupled, and maybe tell us how it is that the internet is loosely coupled, and then contrast that to tightly coupled systems in the utility grid.
Yeah, so on the telephone system, when I was a child, if I picked up the phone and called my grandmother, a circuit was set up and there was a continuous flow of data at a constant data rate between the two ends of the system over one specific circuit. And even if no one was talking, it was there. One thing which enables things to be loosely coupled is storage. On the internet, you can connect links of different communication technologies that run at different speeds because you can store and forward packets, which sort of accounts for the fact that things are running on different technologies and different speeds. So for communication, storage changed everything. Data storage was just as essential as digital communications for being able to move to internet technology.
Yeah, one of the themes here, and I might as well just put an exclamation point on it now, is normal people, even people who think about electricity, I don't think anybody has fully absorbed what a big deal it is to go from a system with no storage to a system with storage. It just fundamentally changes the architectural possibilities. You're like, it's more fundamental than people appreciate, I think. So give me an example of a tightly coupled system.
Well, like the old phone system was tightly coupled where everything was interconnected. And really the old electricity grid was where every customer site was just part of the grid. It didn't have any really functional identity. It couldn't operate separately. So the grid ended at every end use device.
So for every customer to be part of one big pool, that means if I pull on anything in the customer site, it affects everything because everything is part of the same system. Everybody's coupled together. And so loosely coupled means that you get some distinction, right? Functional distinction between these systems such that they can operate somewhat in isolation without affecting one another. Is that fair?
Absolutely. And part of this is the AC frequency of 60 hertz as we use is part of what enforces this in that really things are all very interconnected and all the load affects the frequency.
So one advantage of having loosely coupled systems as opposed to tightly coupled systems, a tightly coupled system, as I said, if you pull on one string, you affect everything. Basically, you can't fiddle with the machine without fiddling with the whole thing. But if you have loosely coupled systems, you can innovate and change and evolve the systems separately and independently.
Exactly.
And that, I think, enables much faster evolution and expansion and scope. And the one underneath that on the list, I think, is similar and related. So entangled technologies versus isolated technologies. Similar sort of concept, right?
Exactly. And this is where the internet technology example is highly informative, where the architecture of the system does this isolating of complexity so that, as you say, systems can evolve separately. So ideally, the technology inside of a customer's site can evolve separately from the technology on the grid, and you can minimize the point of interaction between them.
Right. And so the reason I think that the telephone system was able to make this leap, like one of the reasons you point out, is that we were able to build the new system basically alongside the old system. And like for a while, we had the two systems going, and then we sort of eased our way from the one to the other.
Yeah, so originally, internet communications went over phone lines, as with dial-up modems, and then we flipped it so that with voice over IP, the phone calls went over the internet lines. There's a similar sort of transition from where we are to where we want to be.
Right. What I'm trying to get at here is one of the reasons that the electricity system has not been able to make this similar transition is that you can't really do what you did with the telephones. You cannot build the new system alongside the old system. It is all one big system, and you can't, what's the analogy? Rebuilding the plane in flight type of thing. So that just makes it trickier.
I would actually push back on that. And this sort of gets back to some of the earlier points you made about the podcast with Jonas about his approach to networking electricity and mine. On the internet, there is the wide area network and there's the local area network. The local area network is what's inside of each customer site, whether it's your house or an office building or a factory. And then you've got the modem and router at that boundary. And then the wide area network is everything else. And there's technologies that only exist inside of LANs, and there's technologies that only exist inside of the wide area network. And then, of course, there's things like the Internet Protocol and some other ones that exist in both.
So we talk about entangled technologies versus isolated technologies. And that's a great example, I think, the WAN and the LAN. Like, you can fiddle with WAN's technology, wide area networks. You can fiddle with local area technology, and you don't implicate the one and the other. You can work on them separately, which enables rapid innovation. So as a final thing, transitioning from the unitary to the networked system, and this is, I think, both the most important one and the most difficult for people to wrap their heads around, is going from a deterministic system to a non-deterministic system. What's funny is the reason the telephone people didn't invent the internet is that they were running a deterministic system, and they were convinced that only a deterministic system could work. They could not imagine how a non-deterministic system could do the communications work that telephones did. And of course, they were wrong. People came along, did it, and they faded into history like dinosaurs. Now we're in an electricity, basically the exact parallel situation, which is right now, the people running it are running a deterministic system, and they are convinced that only a deterministic system can work, and they cannot imagine how a non-deterministic system could work. So just tell us, what is a deterministic system and what is a non-deterministic system?
So a deterministic system is where you plan out everything in advance, and then you just operate according to your plan.
Right.
Airplanes used to do that. They used to file flight plans with the FAA. They said exactly the route that we're going to fly, and they had to adhere to that unless they got permission to fly differently, so that the FAA would always knew what they were going to do. And then maybe a decade ago, I don't remember exactly when, the FAA decided, other than these military areas where you're supposed to stay out of, fly wherever you want. And we just transitioned from a deterministic system to a non-deterministic one, and it still works.
And you can imagine if you ran the old airplane system, why that notion would freak you the hell out, right? Like, if you are used to working with deterministic systems, the idea that you're just like all the planes are going to run themselves their own direction and you're just going to sort of coordinate on the fly sounds crazy. And yet it works.
Railroads conventionally are quite deterministic, particularly before where you plan out where the trains are going to be so that they don't run into each other. That's certainly quite important. Whereas car traffic is non-deterministic. When you start driving someplace, you don't tell somebody in advance exactly the route and timing that you're going to take. Right. You kind of make it up on the fly by observing the traffic, maybe seeing what Google Maps says and such.
Yes. To our point here, the communication system, the internet, has become non-deterministic. So as you said, on the telephone system, if I pick up a line, connect to another person, that is a particular physical circuit that the data is traveling to and from. That's not how the internet works. And I don't think necessarily that people know this, so I think it's worth describing briefly. Like, if you send a packet of information out onto the internet, it is not the same. There's not a set path that packet goes along to its destination. So what happens, and how do we make it work?
Yeah, so packets for the same chunk of data, whether it's an email or some streaming video, different packets in that, and there's going to be an enormous number of these packets, are going to take different paths and arrive at different times, and they are reassembled at the end. And if any of them don't arrive, there's ways to retransmit them with TCP to make the whole system work. And to your point about the phone company being blind to this, multiple people went to Bell Labs in the 1950s and said, hey, there's this new thing called packet switching. We think it's the future of communications. And the smart engineers said, yeah, we know that cannot possibly work. And there are people who say it is impossible for a utility to charge a good retail price. And of course, they are wrong also. It is possible for utilities to charge good and better retail prices. They just choose not to. So to your point about deterministic, the wholesale system for electricity has always been deterministic, and my guess is always will be, because that's how wholesale markets work. But retail electricity has never been deterministic. People are trying to force it to be through things like VPPs, but that's not necessary in general for balancing supply and demand. Now, deterministic operation is necessary for addressing distribution system capacity issues, which is its own separate topic that I assume will come up later. But that operates at a totally different scale of a few customers at a time versus millions of customers at a time. And so the two mechanisms operate in parallel.
The idea here is we're going to go to a non-deterministic electricity system. And I think people get nervous about that because, like, if you don't get an email, it's one thing, but like power, home and hearth, your medical machines, whatever, like electricity is very important. So I just think it's worth emphasizing that despite rubbing our intuitions the wrong way, I think, like, I'm not sure our brains are naturally wired to think non-deterministically, but we have found through experience that a massive non-deterministic system can, in aggregate, be as reliable or more reliable than a deterministic system and can scale much faster. But anyway, this is all by way of preface. This is all by way of saying that what you're working on, what you're thinking about, similarly to what Jonas is thinking about, similarly, honestly, to what like you and other electricity researchers have been beating your heads on for decades now, which is trying to take this unitary deterministic system, transition it to a massively coordinated, networked system, and thus reap all the benefits in the electricity system that we got by the similar transition from telephone to internet, airlines, all these other examples you could say. So this is all part of that big transition. And so your basic fundamental point, and the reason we're doing this podcast, and the core thing here is that your contention, your hypothesis, is that if you're going to move from a top-down to a networked system, you can't have top-down coordination anymore. So how do you get coordination? How do you make sure all these loosely coupled systems are operating in concert to produce the desired results? How do you coordinate all this stuff? Your contention is that prices are the only mechanism that can do that at every scale and in every context.
Exactly. I've been looking for the last 20 years for other mechanisms. I've never found another mechanism that can do that any scale at any context.
And so before we jump into what that means and how you envision it working, I just want to sort of like go over what you see as sort of a few of the high level benefits of doing this. Like, why would we want to do this? Why is it worth hashing through how it works and hashing through the trouble? What is the point of the trouble? And so the main thing, which we just mentioned, is that you think it is basically like context and scale agnostic. Price can work for a distribution grid, can work for a microgrid, can work for an individual building, can work for a nano grid inside the building. At every level of organization, the coordination is being done by pricing.
Exactly. And one important point here is that I'm a buildings person. I've worked on energy use in buildings for the last 4 decades. I am not a utility grid person, so I try to resist telling people how the utility grid should operate internally. But I also like utility grid people to not tell buildings people how buildings should operate internally, because that's not their area of expertise.
I actually kind of appreciate that. This is like most of Volt's guests are very grid centric. But your sort of take is like, I got this covered here in my building. Don't mess with me. Just give me my power. Tell me the price. You're not asking much of the grid, basically. Like the grid
Exactly.
needs to tell you what the price is and supply you power. All the other work, all the flexibility work, all the coordination work is done on the consumer side. So this is very consumer centric, distributed building centric view.
I like to use the word customer to make clear that this is applicable to all customer types, whether you're a residential, commercial, or industrial or agricultural.
Right. Another merit of pricing, and this to me is the most compelling reason to use prices for this coordination, is that it allows the customer to accrue all the benefits and the value of flexibility. Like if you get a VPP in there, an aggregator in there, the aggregator takes a cut, 50% around.
Yes.
But if the devices are simply acting flexibly on their own in response to price signals, all of that flexibility value stays with the customer. The customer gets all of it.
Exactly.
You know, when people hear pricing, they think, oh, capitalism, they think exploitation, they think poor people are going to get screwed. You know, like pricing brings up all that stuff. But it should be emphasized, this is a very customer centric view here. This is a view of the grid where customers get the value, reap the most value. Customers are in the driver's seat in this vision and are getting a higher proportion of the value than they would in any other system.
Exactly, yes. This is designed around what's best for customers and customer devices in devices that exist today and will even more so in the future. And so it's designing the relationship between the grid and the customer around what is best for the customer, but also works for the grid. Because remember, we invented the grid to serve customers. We didn't invent customers to serve the grid. I think a lot of grid people don't quite understand that. The customer is supposed to be always right.
And then the third benefit of pricing that I just want to throw out there is, and I think people are not going to be able to really understand this until we talk a little bit about the model and how it works, but this vision of pricing maximizes customer privacy and autonomy and cybersecurity. Because basically, we'll get into the details, but basically under your model, the customer is not sharing any information with the grid above it. And again, we'll talk through how that works. But the point is, like in this model, customer privacy is total. What goes on the customer site is not known by anyone but the customer. And it is not the business of anyone but the customer. So that is as privacy maximizing as you could get. There's no grid. And, you know, third parties can do some work. We'll talk about that later, but there doesn't need to be any third party looking into your customer site. Your devices are doing the work themselves, and they're doing it based on your preferences, and nobody else needs to know or mess with that.
Yes, but the grid does continue to know what happens at the meter, and they should have smart meter readings at whatever time interval, whether it's 15 minutes or 5 minutes, that the grid decides to measure at. So the grid absolutely needs to and should have that meter data and needs it to function effectively. But that's the limit of what they need to know. They think they need to know more, but they're wrong.
Right. And just to clarify, you said this before, but just to clarify for everybody, just so they know, we're talking about retail prices here. We're not, for the moment, we're just leaving the wholesale system, the wholesale energy market, the transmission system. We're just leaving that aside. We're talking about retail systems, coordinating distribution grids. So let's talk about the model. The core concept here with your model is that the grid ends at the meter, meaning what goes on the consumer side of the meter is nobody's business. The grid consults the meter and two bits of information are exchanged. One, what's the price? And then two, how much energy do you need? That is all the grid knows about a particular customer. How much energy do they need? They don't know what devices are in there. They don't know what the devices are doing. The customer is a black box to the grid.
Yes, and my physics colleagues at Lawrence Berkeley Lab, where I was until recently, assure me that the electrons are all the same.
Yes. But this is crucial. So the grid extends to the meter, and the meter tells the grid at this customer site, we need X amount of power. And that is all that the grid knows about what goes on the customer site. The utility is not poking its nose in and controlling your water heater. All the grid knows about it is how much energy does it need.
Well, it's how much energy did you consume in the last time interval? It's after the fact. It's not before the fact.
Right. But it's a quantity, basically. This is the information being exchanged, quantity, nothing beyond that. So let's talk about what you have to have in place to make this work. So to make any of it work, you need what you call a highly dynamic price. There's been a lot of people who discuss this a lot are familiar with time varying prices and real time prices, a lot of other terms for this. You use the term highly dynamic price. What are the characteristics of a highly dynamic price?
Its essence is its hourly prices that are different every day. Specifically, it's prices that have intervals between hourly and 5 minutes. That brackets the range of what's reasonable. You set those prices no farther in advance than the day before, and the prices are different every day.
Okay, let me ask a couple of questions about this. You draw the line at hourly or smaller. Do you get more benefits the smaller that increment is? Or do you think hourly is frequent enough to do the job?
The important reason to start with hourly is that that's very comfortable for people to move into this. And the barrier here is not technology for this. We've invented all the technology we need, all the communication protocols, the price responsive algorithms. The barrier here is the human beings who are fearful of using prices, even though they use prices everywhere else in their life constantly.
You make a point of saying that the prices are different every day. You just mean that they need to be responsive to conditions every day.
Exactly. The conditions on the grid are different every day. So if the prices are not different every day, they are the wrong prices. And it's a basic function of any business to set the right price for their product. And if they are not competent to do that, they need to let someone else who is competent to run a business run the business.
And one other thing is that import and export prices are separate. Explain what that means.
Yes, so I have solar panels and I have net metering, and I pay almost nothing for electricity, even though I derive huge value from the grid because I overgenerate a huge amount in the summer because there's no air conditioning where I live, and I import lots of electricity in the winter. I derive huge benefit from being connected to the grid, but I pay almost nothing. And so other people's bills are higher because I'm not paying enough.
This is the cost shift that everybody's always talking about.
So I don't have an opinion on what the difference should be between import and export prices. But the principle that they can be different and probably should be different, it's a very reasonable tool for grid operators to have in their set of tools. And it's something that devices can readily accommodate and use. And so that's not a problem. But having a stream of import prices, and if different, a stream of export prices, also if you are an exporting customer, that should be 100% of the financial complexity that devices need to contemplate for deciding how to optimize. We should not have things like demand charges, which are, I would describe as evil. They are pathological to good load optimization and to buildings. They were invented in the 19th century. We have far better tools to address the same issue that demand charges are intended to address. We should just get rid of them. They became obsolete a long time ago.
How geographically granular do you envision highly dynamic pricing being? Is this just like a price for a utility area, or is it going to get as geographically differentiated as it is temporally differentiated?
So from the perspective of any individual customer, they actually don't care whether it's millions of people who pay the same price or dozens. Actually, it doesn't affect the customer technology, the communications or the automation as to how locational is what I would call it. So that's really for the grid operators to decide.
But you need to know that to set a good price, right? Because the whole point is that the price is a measure of the value of electricity, and the value of electricity changes from time to time and place to place, and can change place to place, even relatively proximate places, theoretically, the value of electricity could be slightly different between two even relatively close places. So all I mean is like getting the geographic scale right seems important to accurately capturing value.
Yeah, and it's similar to the time interval where there's diminishing returns to getting to smaller and smaller areas,
Right.
and there's diminishing issues about how to treat people, equitably. In California, we are planning to have locational prices, hopefully as soon as next year. In fact, there are some pilot tariffs from the largest and soon the second largest utility in the state that have locational prices today that are hourly. And the size of the locations is several 100,000 people.
Interesting.
And these are areas where the distribution system load shape is different. And so that the reasons for wanting to shift load are different in those different locations.
Right. So, highly dynamic prices. If you want customer sites to optimize based on highly dynamic prices, you have to transmit the highly dynamic prices to the customer sites. So just briefly, tell us what a price server is and what role it plays and why it's necessary.
Yeah, so a price server is like a web server. A web server distributes web pages to computers to show to people. A price server distributes prices to machines to use in their optimization. Now, people are free to look at prices, but we don't want to encourage them to do so because they have much better things to do with their time and they wouldn't be good at using them. But maybe 3 days a year they'll want to look at the prices, and the other 362 they won't, and they don't need to.
Let me just blow that out because we need to make this point generally.
Yeah.
But all of it is meant to be automated. The customer is not going to know or care what the hourly variations in prices are. They're not going to be fiddling with their devices on a day-to-day basis, telling their devices what to do. All of this is meant to be automated and happening in the background. And you, as the customer, can just chill out and take your hot showers and drink your cold beers, basically. Like, I think that's implied, but just to underscore it.
Exactly. But people express preferences in advance as to how they want their devices to behave. And so they can change those preferences anytime they want to.
But anyway, to return to the original point, the point of a price server is just that you ping it and it tells you the price.
Yeah. Or really, actually, it pushes out the data to machines on an ongoing basis. So it's actually technically even simpler than the machine having to ping it when there's a new price.
Right. And this is like the very simple point of this is just that if you're going to have dynamic prices, you need to tell people, you need to broadcast those prices, which is not, might seem obvious, but, it's hard to get information out of utilities a lot of times. So who has a price server? Is there one of these running somewhere?
Yes, the state of California set one up several years ago called Midas, and PG&E, my utility, has one. It uses the OpenADR3 protocol. Southern California Edison, the second largest utility, is going to use the same price server. The state will convert theirs to be using that protocol. The concept of a price server dates back to at least 2006, 20 years ago. It's not a new idea because people recognized early on, if you're going to have prices to devices, you have to have a way to communicate them. So the price server is the essential part. And then you need communication protocols to move the price from points A to points B, C, and D over both the wide area network and then also inside of buildings. And then you need the loads, whether they're loads or batteries or EV chargers, whatever they are, that can use the prices. So those are the three elements.
There has relatively recently been developed what's called OpenADR3, which is a modern, light, replicable, perfectly functional protocol. So we know what a price server is. We have a protocol to communicate these things, and we know basically how to create devices that are responsive to them. But as you say in your paper, there's not yet a place in the world, correct me if I'm wrong, where those three pieces are in place and working together.
Actually, in California, with Pacific Gas and Electric, we do have that. There is a problem with the tariff structure, which is a huge problem that's not worth our time in this podcast, that makes it problematic. So we have sort of the beginnings of it, but we haven't for various reasons, had the ability to scale it yet. But we have the glimmers of it. So California is poised to be the place where this will first happen. But practically speaking, you're correct. There isn't a place. Some places have the prices. We have the price servers, but don't have really good prices yet. Once you have them, then manufacturers will spring up and use them because they can deliver more value to their customers and produce a higher quality product.
Right. All right. So here then we get to, in my mind, the really juicy, interesting stuff. And this is what I struggled with, and this is what I kind of like had a little breakthrough about. So let's talk about the building side. So as we say, the only interface in your system between the grid and the building is just this single point of connection, and the only information being exchanged is quantity and price, basically. So here you are inside your building, your microgrid controller, your central controller of your building devices, which I guess is like a panel, or I don't know what the central controller looks like. I imagine it'll be different for different buildings. So then your central controller receives the grid price. And this is what's interesting to me. So the value of electricity for that microgrid controller, for that particular building, might be different than the grid price. So why is that? What are the sort of considerations at the building level that would mean the value of electricity differs from the grid price? And you call this the value of electricity at the building level. You call this the local price, which could be different than the grid price. So what are those considerations that would make the value of electricity different for a building than what it says on the tin at the grid level?
Yeah, so new solar customers in California for the last 3 or 4 years, they may be buying electricity at 50 cents, but if they want to sell it to the grid, they're getting 8 cents. So what price should the water heater be getting to decide whether it should be heating water for the next hour or not? If you're currently importing, well, presumably you should be getting 50 cents. If you're currently exporting, if it turned on, it would be consuming 8-cent electricity. And so it should be getting that signal so that you consume your low-cost electricity instead of higher-cost electricity. So an asymmetric tariff where the import and export are different is sort of the most obvious and widespread reason to have a different local price. And I used local as in local area network as in IT because we want to emulate IT principles and terminology as appropriate as much as possible.
So whether you're currently importing or exporting will change the local value of electricity. I mean, this is where you could sort of import any sort of values that you want. You know what I mean? Like it might be I, as a customer, place a very high premium on greenhouse gases, on avoiding greenhouse gases. So I can tell my local microgrid controller to sort of adjust the grid price by X amount to reflect that. So then the value of the electricity inside my building is slightly different than the grid price.
Exactly. That's a second reason that can create a local price is taking into account the climate pollution from the greenhouse gases. You simply take that GHG signal, multiply it by the dollar per ton value that you as the customer believe is appropriate, add that to the retail price because climate change is real, and then have your devices optimized to that price. It doesn't change what you pay on your bill, but it changes how your devices shift their load.
Right. And this is key. The point of determining the local value of electricity is not that anyone's paying anybody anything inside the building. It's just to put a value on the electricity. The whole point is to channel power to its highest value spot application within the building, right? And work down from there. So the microgrid controller, your building controller, gets a price from the grid and then translates that grid price into a local price, right? It takes the grid price as an input and then adds whatever local considerations there are and comes up with the local price. And then it sends that local price down to these little individual nanogrids that I was talking about before that are in your building. And this is the fun bit to me. So then that little nanogrid controller takes the local price that it got from the microgrid controller and does the same thing. It says, based on my hyper local considerations, right? Like you might have a nanogrid that's like an EV charger, whatever, in a washing machine, but that nanogrid controller will, based on its hyper local considerations, come up with another local price, an even more local price, a hyper local price, and that price will be used to coordinate the behavior of the devices on that particular individual circuit. This is what I want to emphasize, is this sort of cascade that's happening. And like the price server is sending a price to a building then recalculates to a local price, sends that down to a nanogrid, which then recalculates that to an even more local price. So basically what you're doing, what your grid controllers are doing, your microgrid controllers, your nanogrid controllers, are assessing the value of electricity at that particular time, like literally that particular time and place, and coordinating the devices accordingly. So this answers the question, like, when I threw this out on Blue Sky, a lot of people were like, well, how can prices, like the price is the same everywhere in the building, so how could that possibly coordinate all these different devices? The answer is that the price is not the same throughout the building. In fact, like the value of electricity might, not necessarily, but might differ from nanogrid to nanogrid. But the reason it unlocks something for me is that, like I said, I was getting hung up on the word price, and I just think the word value, at least for my purposes, for my brain, value captures this better. So you're trying to basically compute what is the real-time, geographic specific value of electricity at this particular spot. And that calculation is happening at every individual, like everywhere at every level. So basically, at every level from the very bottom, the most specific device itself, right up to the nanogrid, to the microgrid, to the larger microgrid, the value of power is being calculated at every point in that microgrid, and power is being channeled to the highest value uses. I want to get people thinking about value rather than price, because the whole point of this is to make sure that the power itself goes to the highest value uses. Hey there, everybody. Don't worry, I'm not going to tell you about a new mattress or push a credit card on you. This isn't an ad. There are no ads on Volts. It is supported entirely by listeners like you. If you'll indulge me for a second, I'd like to ask for your support. I started Volts because we're all surrounded by depressing news about climate change and misinformation about clean energy, and it's never been more important to share the stories of the real people on the ground doing the real work of transition, and all the ingenuity and courage and public spirit they are bringing to it. People are hungry to hear these stories, to learn from and find inspiration in them. I've heard from people who changed majors or careers after hearing episodes of Volts. People using it in classrooms and community groups, even state legislators who have passed bills inspired by specific episodes. Sharing these stories matters. It makes a difference. If you have found value in it and want to help me continue doing it, I hope you will join the community of paid subscribers at volts.wtf. It's about the cost of a cup of coffee a month. If you don't like subscriptions, you can make a one-time contribution, leave a review on Apple or Spotify, or just tell a friend about Volts. I am grateful for any and all support. If you're already a paid subscriber, thank you. And now, back to the show. I want to get people thinking about value rather than price, because the whole point of this is to make sure that the power itself goes to the highest value uses.
Yeah, so price is just the unit of measurement by which we measure value. It's dollars per kilowatt hour, and that's what you use for any of these, so long as you're in a country that uses dollars. So it's always that same unit that you're using, no matter what the scale is. My house, where I already have several price responsive devices, I don't yet have a local price because I have net metering and I haven't set it up to take into account the greenhouse gas. So most customers will start out with this using the straight import retail price, and that's fine. That's the starting point. But the communications and automation technologies facilitate this more rich utilization of it trivially. That's just part of how it works. And so you get all that for free.
One thing I think is important to point out here is that your building is calculating the value of electricity to you individually, your considerations, your local considerations, and acting accordingly. That is something that a VPP can't do. A VPP is going to round up a bunch of devices or a bunch of houses and basically treat them as a class, as all the same. A VPP can't, by its nature, calculate what is optimal for each individual customer, right? Only prices can do that for you.
Correct. The VPP doesn't have access to the correct information to make the right decision, but also the VPP is acting first for its own interests, second for the interests of their customer, which is the utility grid, and only thirdly for the actual electricity customer. With price responsiveness, 100% of the value, as you mentioned, goes to the customer, and 100% of the control is with the customer and the customer devices. Now, customers may choose to have a third party optimize, let's say, their thermostat. And that could be the product manufacturer, it could be someone else, it could be a nonprofit, it could be the electricity retailer. And that's fine. And they might even pay a small subscription fee for that service, but the customer is always in control. And the optimization is 100% for the value of the customer because the customer is engaging that third party for the customer's benefit. But so the key is that if we only had VPPs as an option, I would be an enormous fan because they do deliver important value. And there are some things that VPPs do that price is not the right tool for and shouldn't be used. For example, emergency load reduction. If a power plant or transmission line fails and the grid needs an immediate, within 1 to 2 second drop in load, that's a great use of VPPs, and that's not something you would do with pricing. And there are other things like that around the edge that are great uses of VPPs. So it's not that we shouldn't use them, we should use the right tool for the job. And part of the right tool is the most cost-effective tool.
Right. So here we come to a key question, which is, okay, the grid comes to my meter, tells me a price. My building microgrid controller takes that price as an input and computes the local price, and then optimizes my devices on my site, on my consumer site accordingly. So like, what does it pay? How does it negotiate? Do you know what I mean? Like if the price is different, if the local prices or local value is different than the grid value, what happens between the grid and the meter? There's presumably some negotiation.
So the grid only sees the meter readings and the price that the grid announces and then computes the bill. That's how the only involvement of the grid for balancing supply and demand. Now, there is the related topic of capacity, but putting that aside, there's no negotiation. And all of this local price stuff is completely invisible to the grid.
So the customer side is computing based on the local value of electricity to me at this moment. Here's how much I need, and here's how much I'm willing to buy at this price.
Well, I mean, the optimization could be in the central controller or in the individual device. And most buildings will use both of those, or in the cloud.
Well, this is something I wanted to ask. Like, do you need the central controller? Like, if the devices are smart, couldn't they just do the work? Like, is it necessary that you have a central controller?
It's not if the retail import price is all you need. Then you can just send that price directly to devices and they can use them. So yes, you do not need it. You will want it over time. And the transition from having no infrastructure to infrastructure devices is a common one. With cable TV, originally the cable went directly into the back of the TV, and then we moved to have set-top boxes, infrastructure devices that sort of decoupled between the two domains. And then, of course, with dial-up modems, your computer was directly connected to the internet. And then now we connect to our local area network through some switches and routers to the modem, and then that connects to the wide area network. So creating infrastructures is natural, but to your point, you don't have to have one to start using it so long as you're just optimizing to the direct retail price, which with better prices is going to be much better than what occurs today. And so we can do this transition incrementally and organically. It doesn't have to be an all-at-once thing.
So say I'm in a neighborhood. By nature, my neighbors will be experiencing the same climate as me, the same temperature, whatever. They will probably be roughly comparable to me socioeconomically, whatever. So like our price comes to our neighborhood, and then all the devices, all these customer sites take in that price and then act on it. But presumably they're all going to be making roughly similar calculations, and they're going to all act roughly the same way. So say, for instance, like a cheap electricity price comes down 1 hour, and then every EV charger in the neighborhood is like, hey, cheap electricity, let's charge our EVs. Boom, they all go start charging EVs. You get a massive surge and you overwhelm your neighborhood transformer. In other words, how can a single price that's going to a neighborhood cause individuals in that neighborhood to act differently? You know what? It seems like they're going to act as a school of fish, and that's going to cause all kinds of capacity problems.
Yeah, so there's several things are going on here. One is that if you have a precipitous change in price, you're likely to get a precipitous change in demand. And many utilities around the US and around the world see this with, TOU timer spikes, where, to your point, EV chargers are all set to start charging at midnight. And so you create this problem not only locally, but also for the macro grid. And so the answer is don't have a precipitous change in price. And if you have, these more fine grain of hourly or half hourly prices, then you can have the price change slowly, not dramatically. But even within the EV chargers, different cars will need to charge for different amounts of time and need to be complete at different times of the day.
But will they, though? Like, they're probably all going to work in the morning, and they're probably, most of them, coming home in the evening. Like, this is what I mean. Like, their behavior is going to be roughly similar.
Maybe one needs to charge for 2 hours, one for 3, one for 5, another for 3, so that if there's a trough of low price times, then the utility needs to just set the size and shape of that trough to result in the load shape which is best for the grid. Prices should be set based on the result that they produce for the grid, not based on the state of grid infrastructure. Utility people commonly assume that you must set retail prices based on cost causation, which is just wrong. They don't know that it's wrong, but it's wrong. Prices should be set to produce the right result. That's what airlines do. They don't charge prices based on the state of the infrastructure, their airplanes and their staff. They set it based on past experience with how customers buy tickets by geography and calendar, et cetera, and then set prices to maximize the most benefit for them. So utilities should set prices for all of their considerations, for generation costs, for transmission issues, distribution issues, environmental goals, et cetera, produce the best load shape, both in aggregate and also by these locational areas. And that will have a loose relation to things like wholesale energy costs, but will not have a tight relation.
So first, like, I'm not sure everybody's going to understand the distinction here. So the two separate questions here are how to distribute power, and then what happens if like particular circuits are overloaded. In other words, the capacity of the circuit to handle. So again, like a price signal goes to the devices act a certain way, they overload the circuit. What tools do you have to keep capacity in safe boundaries? Like if you charge an EV, it is a large power draw rapidly, basically like a big burst of draw in a way that like a stove or an air conditioner or whatever is not going to be. Especially if you have like a DC fast charger with multiple stalls, like if 3 EVs hook up all at once, all of a sudden you got a ginormous demand out of nowhere almost instantly.
Or if you have a pole-mounted transformer with 10 houses, 6 of them have EV chargers, and maybe one of them has 2, you can easily get the same thing. So for my house, on an annual basis, well, ignoring my PV panels, it uses about 1 kilowatt on average over the course of the year. The highest single hour was a little over 4 kilowatts for everything before I got an EV. And then an EV charger can be 7 or even 9 kilowatts all by itself.
Wild. So running your EV charger more than doubles the previously high point of your instantaneous load.
Yeah, for the highest single hour, and it could be like 8 times the typical. So that's incredibly bursty.
Right, it makes it a new kind of thing on the grid. Like this is, I think, is also worth emphasizing. Like it's not like we have a lot of experience dealing with giant bursty loads. There just haven't been a ton of them.
The first place that this capacity issue showed up was in Australia, which to a recent podcast of yours on rooftop PV there, they, a number of years ago, had an increasing number of circuits where on certain days in the afternoon, when solar production was at its peak, the transformers and wires were approaching their capacity. So they said, okay, nobody else on this circuit gets to install PV, forever, unless we spend lots of money increasing the capacity of the system.
Or they can curtail. Now they're writing that into the contract that they can curtail your individual solar in these circumstances.
Yeah, rather than saying no one else can install solar, when in fact most of the time there's extra capacity. It's only a few hours of the year. What they started doing was broadcasting out interval power limits to each customer, not to how much the PV can produce, but to how much the customer site as a whole can export. This is called dynamic operating envelopes. And then they can fairly allocate the capacity to each customer, and it's different for each customer, different every day, to make maximum use of the capacity that's there and guarantee that the system will not be overloaded. So that's an incredibly powerful mechanism.
So an individual customer site is told, here's how much you can export this hour.
Correct.
And so if its solar is running, it might take this and say, okay, well, then instead of exporting all the solar, I'm going to put it in my battery. That's the kind of calculation that's going on the consumer side in response to this.
Correct. Anything that you might have been in danger of having to curtail, you instead put into a battery, you run the air conditioner, you heat some water, whatever it is. And we want people to shift load at those times anyways. So this mechanism just reinforces what's good for the customer and good for the grid as well. There's no financial aspect to this. It's purely a requirement for operating to make sure that we keep the system safe. And doing this kind of digital capacity management is not new. USB, which has now been around for more than a third of a century, which I think is amazing to think about, from day one has had capacity management. You plug a device into the USB port in your computer, it can't just take power, it has to first request capacity. And so there's a negotiation about the capacity. And so this is fundamentally different from the pricing, where the communication is one direction. For the capacity management, when you get to things like EVs, there does need to be some sort of negotiation so that the grid can allocate through some dynamic mechanism capacity, and then devices are able to reserve capacity when they need it and plan for it and guarantee that the system will not exceed it. And the details of that mechanism are still sort of being determined. People have different theories, and we absolutely need to do more experimentation on that. Pacific Gas and Electric and Southern California Energy in California are doing experiments with some mechanisms. They're kind of more Band-Aid rather than permanent ones. The protocol you mentioned, OpenADR3, has 2 mechanisms for it. So this is an area that needs much more attention, but it can be done in coordination with the customer site as a whole, rather than trying to micromanage individual devices. But what happens at the meter is the only thing that actually affects the grid. It simplifies things so much if that's the point of interaction, rather than trying to work around the meter because you don't have the right arrangement of the meter.
Right. The take home here is you've got 2 separate mechanisms, basically, pricing mechanisms and capacity mechanisms. And according to you, once you've got those 2, you're mostly done. You need to send out price signals, and then you need to send out basically capacity envelopes that people need to stay inside. But with those 2 bits of information, what is the price and what is the hour, what is the sort of capacity envelope for the hour? That's all the information customer sites need to do their optimization and to do collective optimization, basically.
Correct, yes.
And this capacity, this will also be a relatively local thing too, or generally these capacity issues come up on individual like transformers or?
Yeah, it could be the first transformer in front of a house, for example, or it could be a substation or the wire in between. So it could occur at different points in the distribution system, depending on the details of it. That's all inside the grid. Where the constraint is doesn't matter to the customer. The customer only needs to know what's the mechanism for coordinating with the grid so that things work out the best possible for everybody, which is to use all the capacity that's there and guarantee that it's not exceeded.
Okay, so here you have, and this I think is what comes up with a lot of people when they first hear this. So here you have a system that's based almost entirely on price. Basically, like, how much does it cost? Who can pay? And when people hear that, their mind goes immediately to, well, what about people who can't pay? Like, how is this not sort of like rapacious capitalism, et cetera, et cetera? So I think there's a question of like, if price and capacity are your two mechanisms and your only two mechanisms, how do you ensure other kinds of social or political, goals or guidelines? How do you layer other stuff in?
Yeah, so I care as much about this as anyone else does. When I started thinking about this, I started thinking about it in the context of off-grid systems in developing countries and how to make that work. And that's how I originally came to be using price. But simply changing the price does not increase system costs. In fact, changing the price is a way to reduce system costs and therefore reduce bills. And so that has to be clear in people's minds, is that dynamic pricing is about achieving lower bills. It's not about achieving higher bills. In California, what we are doing for the near term and what we should do forever is that you charge an hourly price and you calculate the bill according to that and according to some TOU price. And if you would have paid less under the TOU, you pay that to make sure that the people who today are more expensive to serve than others continue to pay the TOU, and the people who are less expensive to serve and then also can do additional load shifting pay the hourly. And over time, more and more people will just be doing the hourly, and fewer will be on this TOU backstop. And that's easy to understand and easy to implement.
How do you protect low-income ratepayers?
Because they continue to pay the TOU if they are more expensive to serve. Many low-income people today are less expensive to serve and are paying more than they should because they're consuming more at the low price times. Others are the reverse. So it's not like low-income people are some monolith. The current system is not fair. We have to recognize that. Current tariffs are not fair, absolutely. And if we want to make things fair, we can move in that direction and move it in a way which protects anybody who has non-optimal load shapes, and then we can help them change their load shapes through acquiring devices, controls or new appliances, like we've done with energy efficiency for decades.
Is there any functional distinction between an individual customer site, a building, say, that is its own small microgrid, and a larger microgrid in which that building is a part? Like, to the larger grid, the microgrid is the black box, right?
That's absolutely true. And this community is essentially a single large customer from the perspective of the utility.
That's what I'm trying to get at. Like, theoretically, a whole community could be, from the grid's point of view, a single customer if they were all on the same microgrid.
Correct.
And then they could calculate their local price based on their local values.
But that's the retail price for that community. And that would be, at best, a locational retail price. It's still not a local price inside of a single customer site. So they're similar, I can see that. But you still have a utility customer relationship between the community and the final customer. And that's not a problem. That's not the same as inside of a customer site.
Right. The whole question is like, how do you allocate your power to your highest value? How do you allocate power? And the way you want to allocate power is you want to put it where it's most valuable first and work down from there. And so to do that, you need to calculate, well, what is the value? And the key insight here is that the value from the grid perspective is going to be slightly different than the value from the building perspective. So value is being calculated all the way down such that when you get to the device level, the actual device optimization is working on extremely local, very specific value information. And so you are optimizing for value at every level.
Correct.
That, I think, is that's the point here.
Yeah. And the water heater doesn't have to know where the price came from or why. It only cares about what the price is. So the grid could go down. Your house continues to operate as a microgrid because you've got a battery, and the price may change. And so the water heater reoptimizes. You may have a higher price or a lower price, depending on what's going on. And the water heater doesn't care about why. It just cares what the price is. So All of this topological complexity in no way affects how devices operate.
Right. And let's return briefly to the point about non-deterministic systems, because I think now that we've sort of described how this works, how price is being used as a coordination and optimization mechanism down to the device level, in what sense is this system non-deterministic?
So retail customers have always been non-deterministic in their consumption of electricity, with, I'm sure, a few niche exceptions. But in general, you don't promise in advance to your utility grid how much electricity you're going to consume each hour for the next month or the next year. You just consume whenever you want to. That's always been the case about how electricity works. I'm not changing that at all. We can either charge bad prices or we can charge good prices. Now, what's a good price? A good price is a price which results in a better overall situation for the grid. The entity is that's setting the prices. That's their job, is to set the price which produces the best result for them. In the past, the price was just a revenue generation mechanism. That's all it was. In the present and future, the price is also a control mechanism to shift load. And so what you need to do to set retail prices in this context is you go through two separate calculations. One calculation occurs today, which is the revenue requirement of the utility. How much revenue do they need to collect at the end of the day, month, or year? And this doesn't change that one bit, except that we will lead to needing less revenue because the system can be more efficient. And then secondly, you go through a calculation of what's the shape of the prices, 24 hourly prices or 48 half-hour prices. And the grid, based on past experience, determines what shape for this locality will produce the best result for the grid, and then shift that shape up or down so they collect the right amount of revenue. And those are two things happen in parallel so that you meet both objectives: collect the right amount of revenue and charge the right shape so that the right load shifting happens. And in general, the water heater, because you're only shifting load, you're never shedding load with your water heater, only cares about the difference in prices. It doesn't care about the absolute price. And so these two things work seamlessly together to shape load and to collect revenue.
I guess I come back again to, how this is going to produce a more efficient system. And I think one of the advantages of this is that it makes flexibility not something that you try to add on top of the system, or that you try to tweak the system afterwards. Flexibility will just be part of normal electricity consumption.
Exactly.
Basically, in this. Like, the flexibility is part of the operation of the system, not some separate thing.
Precisely. So historically, what we do is we sold electricity at the wrong price. The utilities got results that they didn't like for whatever reasons, because it, too high of generation costs, transmission or distribution issues. And then we created these complicated, expensive mechanisms like VPPs to account for the fact that we charge at the wrong price. And so those are expensive bandages on the system, or like digital paint on the old analog system. What this is, if you charge the right price to begin with, then you get the result you wanted. You don't need the Band-Aid. You don't have a wound that you need to address, because you're not creating the wound by charging the wrong price. And in other contexts, we just charge the right price. Airlines charge the right price. They don't sell their tickets at a flat price and then have third parties go in and try to convince people to change their flight times to even out the supply and demand of airplane seats. They just charge the right price to begin with.
This is the analogy that finally occurred to me. I was thinking about how to explain this to normal people, and this is the analogy that I think works. It's like, imagine if airlines sold all seats on all flights for the same flat price. They would get terrible results from that, right? Like, some flights would be massively, oversubscribed, some undersubscribed. So imagine a third party came along, rounded up all the ticket holders, and said, hey, the airline's getting terrible results, and there's some value to the airline of you being flexible. So can you move your flight, like individual customers? Can you move your flight? And then that third party rounded up all the customers, took their flexibility, and sold it to the airlines, basically. That is the VPP model.
Exactly. And it's complicated and it's expensive.
What you are saying is, just don't charge that dumb flat price in the first, don't charge the wrong price in the first place. If you charge prices that reflect temporal and geographic value, you will get the results you want, and then you won't have to do this ad hoc flexibility stuff afterward. Is that fair? Like
That's fair.
the airline analogy, you think that works?
Yeah, and the key difference in the last few years is that we now have all of the technologies at very low cost, often free, to make the automatic control highly practical. We have the communication protocol, which we had communication protocols for pricing, for the last 20 years, but they were old and cumbersome and difficult to deal with. Now we have modern, simple ones. We have, pervasive internet connectivity so that devices can get the prices. We have extremely low cost computation on integrated circuits. The integrated circuits that go into appliances that cost $4 or $5.
Yeah. This is worth emphasizing. This is all cheap.
Often free.
Like the benefit of all these electronic development over the last 30 years is like, this is all just basic circuits and like communication stuff that is trivially cheap. It's not some big, fancy, complicated stuff we're talking about. Your water heater just needs to ping the internet, and that is a solved problem.
Yeah, and ping your local price server in your central building device to get the price.
Who is then pinging the
Exactly.
Who is then pinging the central price server?
Yeah. So the reason so many appliances have Wi-Fi on them today, when you think, does my dishwasher need to have Wi-Fi? Well, no, it doesn't. But the microprocessors have Wi-Fi and Bluetooth on the chip, whether they are used or not. So it is literally free for them to include it. And you can't get much less expensive than free. I have I will soon have 3 price responses today, covering my space heat, water heat, and EV charging. And also my phone optimizes to a GHG, all of it through free software upgrades from the manufacturer for devices that were not grid responsive when I bought them.
No kidding. So you bought non-grid responsive appliances, and it's just they had the chips in them that were capable of Wi-Fi communication. They just, because they sort of included trivially regardless. And so a software update from the manufacturer then turned on its ability to communicate with the web?
I should be more specific here. So my space heat and hot water come from a heat pump, which the heat pump can't communicate, but I have a clever controller, commercial product. When I bought it, it optimized to time of use prices in the manufacturer's cloud. I then got the free software update where it optimizes to hourly prices in the controller in my house, and it receives those prices that were open ADR3. That was a free software update. The EV charger, when I got it, it optimizes to TOU prices in the cloud, and they are working on integrating with the PG&E price server to be able to use the hourly prices and optimize in their cloud to it. And that PG&E price server uses OpenADR3.
Really, most of what you're talking about in this system is software tweaks. Like, there's just not a lot of hardware, certainly not expensive hardware, involved in any of this. Most of this is software.
Correct. So for any new product or any product that you can get a over-the-air software update, an increasing number, this is pretty trivial. There is this long transition time where lots of people have old water heaters, maybe it's an electric resistance water heater, and there are commercial products today that will control them and are internet connected and could readily operate to an hourly price just as well as to the TOU price they're operating to now.
So there's no barrier to making literally any appliance price responsive. Even if it's dumb and old, you can get a controller to attach to it to make it.
Well, a dumb device, generally, it only works if you can depower it. And so for a resistance water heater, you can just shut off the power to shift its load. I'm sure there are some devices where that's not a workable option. So some devices will need replacement, but many devices have these external controls, which do cost something. But doing anything costs something. To have something be part of a VPP, it has to be able to communicate, and that's all you need for the price response. So you don't need anything more for price response that you need for VPPs. You just avoid a whole lot of cost and complexity.
Let's talk about how to get from here to there, which is part of what's broken my brain about all this. Like, this is a very wholesale change in the way the electricity system works. So just to review, what we need to make this work is a central price server, a protocol that helps communicate, and price responsive devices.
Yes.
We have price responsive devices. That's a solved technical problem. We have the protocol. That's a solved technical problem. We know how to make a price server. That's technologically trivial. So, technologically speaking, this is all good to go,
Yes.
basically. So, it's not technology development that is the barrier here. So, I guess what is the road in this direction? Does it start with utilities changing how they charge prices, just with utilities implementing more dynamic prices? Is that step one here?
That's step one. And it could be like either a unitary utility, either acting on its own, or it could be a utility forced by a regulator, such as in Illinois, where the legislature passed a law saying they must offer hourly prices different every day. And they've had it for 10 years. And
oh, really? So Illinois has highly dynamic prices of the type you're talking about.
yes, but the variation over the course of the day isn't very much, so your opportunity to save is limited. It's there, but it's not that great. And they have only very limited automation. They don't have a price server in the way that we're talking about. But to your point, having the prices is sort of a prerequisite for everything else, the prices and the price server, because, well, it's not that difficult for manufacturers to put in the ability to be price responsive. In general, they are reluctant to spend time doing so until they have a critical mass of customers who could actually use them. I've had this conversation with many manufacturers over many years, and they say, well, I'm not going to innovate into a vacuum. I need to have a business case. I need to have the customers, and the customers need to be able to pay the prices. So everything comes down to the prices. It's not a chicken and egg thing. The prices have to come first.
Yeah, but I mean, like, skate to where the puck is going. Like, everything's going to talk to the internet eventually. Like, just go ahead and do it.
Yeah, and then we also need to get global consensus on the maximum complexity of the tariffs as it affects device optimization. And just to be clear, you can have fixed charges which do not affect device optimization, but the parts of the tariff that affect how devices optimize to reduce bills the most, that needs to be limited to the stream of import prices and stream of export prices. And that people need to recognize needs to become the global standard so that somebody in a manufacturer in China shipping products all over the world can ship products that will work all over the world because everything works the same way.
I see. So you want to standardize price format, basically, to make this replicable and interoperable across different utilities, different countries, different
across everywhere. We've done this with IT technology. It's not like we haven't done this globally before. And we just need to get a critical mass of organizations that operate according to these principles, and that other people will see the merit of it and then be consistent of it. So it's really the question is, how do we get to that initial critical mass? And if you take the principles that things should be simple and universal, you're 80% of the way towards having the right answer. And of course, some utilities will think they're special and different. And of course, you and I know they aren't special and they aren't different in this respect. Now, how you calculate the price, that can be different everywhere because that doesn't change the communication. This is just like web browsing where you've got the web server, HTML, and web browsers. And HTML defines the maximum complexity of the web page. This price structure defines the maximum complexity of how prices should be done on a retail basis.
Got it. But it's a high priority for you to keep this simple, to keep the pricing differentiation as simple as possible.
Exactly.
Import price, export price. But it is going to change hour to hour. So it's not simple in that respect. It's changing temporally all the time.
And also, it could be a day. The vast majority of people who pay such prices, they're day ahead prices, and that's absolutely the place to start. But once people have the automation, they'll realize that you could shift from day ahead to day of prices, and the communication and the automation don't change. And that's going to result in a slightly lower bill. This will happen later on, but we just have to know that the devices don't care if it's day ahead or day of. But the key thing here is that we don't want to put digital paint onto our 19th century electricity technology. We need electricity technology initially just inside of buildings and then later into the utility grid, which is digitally native and networked, instead of using network technology to manage our 19th century systems.
So, this is a very big set of ideas and topics, a very big idea. Do you have a sort of next thing that you are pushing for? You said we can step toward these incrementally? Like, what's next on your personal list that you would like to see happen moving in this direction?
Aside from every electricity retailer offering hourly prices that are different every day, or something that's beyond
I mean,
flexibility.
that's kind of a big step, Bruce. I mean, much more practically earthbound. Like, is there a particular utility you're trying to get a pilot thing started with? Like, I mean, like very practically, what needs to happen?
So PG&E offers hourly prices different every day to any customer type today and has for more than a year. And Southern California Edison is supposed to soon. And the state of California's Energy Commission policy is that every Californian should have access to such prices in less than a year. Now, I don't think we'll make that deadline, but we are trying to get there.
And that's the price server that you're talking about. Making them available to everyone is just about setting up the price server,
it's about
right?
offering the prices and having the price server to communicate them. Because in some places they have the prices, but they don't have the price server.
Let's just stipulate in our fantasies, 2 years from now, California has the dynamic prices, has the server. Then what's left to do for Californians, individual consumers, is just to buy the price responsive devices, right? Like everything will be in place except for the consumers.
In many cases, people will get devices that can get software updates to do it, or they can acquire a central controller that can do it. And when they replace a product, they will replace with one that does this. And any cloud connected device can certainly do this and just optimize in the cloud. So there's lots of paths for many existing devices to become price responsive very quickly. And then it will take time for most of the devices to turn over and get replaced.
But long story short, California is moving in this direction. And there is reason to believe that in some amount of time, 2 years, 5 years, this is how the California electricity system is going to work.
Yes. Now, we also plan to still have VPPs and use them both. And the balance of it should be really just determined by the market and the need. And again, there's always going to be some, we will make good use of VPPs for the foreseeable future because we won't turn everything over instantly, that there'll be just a shift in the balance over time. And there are some limited services that VPPs are better at. So it's not that they don't have a role, it'll just be changing. I was thinking the other day that it's like hybrid cars. Hybrid cars are sort of like VPPs and that they're kind of a Band-Aid solution. And hybrid cars are actually growing, as I understand it, even as electric vehicles are also growing. But over time, eventually the EVs will grow and start taking up, and the hybrids will decline over time. So that's, I think, a very good way to think about it also.
The point I'm trying to make here, and what I want listeners to take away, is that this is not just like Bruce's elaborate fantasy that he's concocted. Like, this is a thing that's happening in the world.
Yes.
There are systems that are moving in this direction, and this is something that could actually happen within our lifetimes. We could see a system working.
Millions of people in at least 20 countries pay such prices today. Unfortunately, most without the right automation. And the automation is really easy to set up. And so the barriers are really all in people's heads and institutional. They're not remotely technological.
And maybe this is a hard question to answer, but among the sort of nerds who think about stuff like this, the class of nerds in the world who are beavering away, investigating electrical systems and thinking about how to reform them, is there a broad consensus behind this basic vision, or is it a battle? Is it a debate? Are you an outlier? Like, are you a minority? Like, sort of what's the state of opinion in electricity world about this? Like, are a lot of people captured by this and want to move this way, or do you feel like you're sort of fighting the tide?
Well, I feel like I'm fighting the tide, but there's lots of reasons to be optimistic, at least in the long term. More and more places are offering more dynamic prices. The automation of their use, people haven't kind of figured out that that's an essential part of this. And the desire for privacy and autonomy certainly, I think, is only growing, and the desire for lower bills is growing. And of course, both of those are facilitated by this. One problem here is that there's no group of companies that are making lots of money off of this that are a trade association lobbying for this, because the customer saves the money. And so there's not these companies pulling money out. That's part of why this is so good. So with VPPs, you've got tons of venture capital, so they can have big PR budgets and get lots of attention to this. Whereas there's no industry behind this for pricing, because it's all about saving money rather than about extracting money from people.
Yes, it is a value shift in the direction of customers. And sort of like, as a cynic, you would sort of expect that not to be hugely popular among the entities who were previously receiving that value. You know what I mean? Like, what you really need is like consumer groups to get behind this. And this gets back to what I was saying earlier, like consumer advocates, when they hear, let's just throw everybody out on the mercy of the market and to use nothing but prices, have negative connotations around that. So there's a lot of communications work to be done with the consumer field about this, about why it's consumer friendly.
We're already at the mercy of the market. We're already paying all of the revenue requirement for utilities. All this does is reduce how much revenue they need. And it's a way path towards lower bills. It's not a path towards higher bills. That's the key.
Yeah, I know that. You know that. But like, I don't think ordinary people, when they hear pricing, necessarily think consumer first, which is just to say that like there's a lot of translation and communication work to be done here to help people understand why this is a consumer friendly reform and not like rapacious capitalism or whatever.
Yeah, and internet technology developed from researchers and academics and government labs and such. It wasn't in the market where it all developed because it had sort of business backing until it reached scale, and then people figured out that they could have businesses around it. But the development wasn't driven by those business interests. And so that's the problem here, is that we don't have business interests driving the development of this, even though once it exists, people will realize there's lots of opportunity to change existing products or introduce new products.
Obviously, like, we've barely scratched the surface. People can go to your website, got all kinds of papers digging into this further, all the ins and outs. But I guess one thing I just sort of leave listeners with is, and this I think is a good provocative question you ask, which is, if not prices, then what? As you say, like, VPPs are good, but customer sites are going to get very complicated. And trying to micromanage whatever, 10,000, 50,000 customer sites from a central location is just going to get impractical quickly. Like, we need a coordination and optimization mechanism that can operate locally, basically, that can operate at different scales, that can operate off-grid or on-grid, et cetera. And I guess if not pricing, then what is that going to be?
Exactly. And I've looked for 20 years and I've never found a second mechanism. And let's suppose that the utility sees their transformers getting overloaded and wants to turn down my EV charger, but I really want to charge my EV, and I've got a stationary battery I could discharge. They shouldn't turn down my EV. They should just say, you can't import as much power, in which case I'll just discharge it from the battery and keep charging my EV. So all the decisions need to be made locally, because the information to make the right decision is local, and the customer's preferences and economic impacts all occur locally.
Right. So the customer is in control here, in the driver's seat here, getting all the value of flexibility, in control of the preferences, in control of the operation of their devices. So all of that, it is one thing I like about this sort of vision, is that you sort of have solved the privacy problems at a stroke here, and kind of the enshittification problem too. I think this is going to avoid that too, because the utilities are not capturing you. The VPPs are not capturing you. You are running your own stuff.
Yeah, because it's platforms that enshittify. It's not technologies.
Yeah, right.
And you're not required to be part of any platform with this. It's only about technology.
Yeah. Okay, well, I'll leave it there. Good Lord, thank you to any listener who's still with us. Thank you, Bruce, for walking us through this. Again, people can go to brucenordman.com and learn a lot more about all this. Thanks, Bruce.
Thank you so much. And I would love to hear from other people who want to have questions or want to help out with this.
Thank you for listening to Volts. It takes a village to make this podcast work. Shout out especially to my super producer, Kyle McDonald, who makes me and my guests sound smart every week. And it is all supported entirely by listeners like you. So if you value conversations like this, please consider joining our community of paid subscribers at volts.wtf, or leaving a nice review, or telling a friend about Volts, or all three. Thanks so much, and I'll see you next time.